Hello and welcome back. Welcome back to another one of these videos where I ask myself why a number is interesting, right? But why? So today is June 26th, June June 26th, 2023. And I'm using last time I was using something there was like a thing where it was a delay where I would write and then you would see my reaction to what I was writing. So this time I'm using the Google Jamboard, which I don't know why I held this up. This is a Trois Brasseurs coaster. So I'm being sponsored by Trois Brasseurs and the Google Jamboard. I'm kidding, that's just a joke. Um, one of the very many jokes that I will be telling in this video. But no, okay, seriously. Today, what we'll be looking at is we'll be investigating why the number, why the number 25 is interesting. Or I guess cool. I don't know what I called this video. Maybe cool or interesting. What did I call 24? I think I said cool. So why is 25 cool? Why? Well, this video is going to be all about triangles, okay? And in particular, right angle triangles. Okay, so the answer in one or a few words is, oh God, oh, what the hell happened there? No, go back. Oh, okay. Right angle, right angle, triangles. Okay, so what do we mean by that? Let's consider this right angle triangle here, right? So it's got a 90-degree angle here, which is un angle droit in French, and I'm directly translating that to a right angle. Hopefully that's correct. Um, so we have a right angle triangle, and now um, consider the instance where two of its sides, so this side has length 3, let's say 3 meters, and this side has length 4 meters. And this very special side, which has a very special name, the hypotenuse. I really hope that's how you spell it. Well, it is if it's in French, hypotenuse. So if it's in French, then I know I'm right. So you have this right angle triangle with uh, um, uh, side lengths 3, 4, 5. And there's this amazing property um, by the name of the Pythagorean theorem. It's actually a theorem where, in fact, if you take the sum of the sides which aren't the hypotenuse, so 3 and 4, and you square each of those sides. So you take the square of each of those sides to 3 square, 4 square. Well, what does that give you? That gives you 9 plus 16. And what is 9 plus 16? That's 25, which is today's number. And that's interesting. Why? Because 25 is actually 5 square, which just so happens to be the length of the hypotenuse here. And this is not a coincidence, okay? It's not a coincidence. It's actually a very well-known and very ancient theorem that goes back to, you guessed it, Pythagoras himself. So I'm saying his name in French because that's how I learned it. But I guess Pythagoras, I don't know. It doesn't matter. Um, and so what does this theorem say in general? It says that, if you have a right angle triangle like this, and it has sides A, B, and C, then you will have that the sum of the sum of the length of the sides square, which aren't the hypotenuse, is going to be equal to the square of the hypotenuse. okay? And that's a pretty cool result, okay? And in fact, the very first triple of integers, right? The first triple of integers, right? So we're only talking about whole numbers that, let's say, respects this property is 3, 4, 5, right? Where, 3 squared plus 4 squared is equal to 5 squared. And um, this is one of the reasons why 25 is cool, and the reason why the reason I chose in this video. There's a bunch of other reasons why 25 is cool. I think don't really I haven't looked at in other angles. I think there's like this place where there's like a PDF, and you just go on it, and it tells you a bunch of the reasons why 25 or each number is cool. Um, and I may or may not link it to this video. I don't know. Nah, doesn't really matter. But in this case here, the reason why 25 is cool is because it's part of the first Pythagorean triple. Okay. And what I'd like to do in the remaining time I have left in this video is prove to you why this property holds. So what I'm going to do now is I'm going to prove this to you. That is, I'm going to prove to you in general that if you have a right angle triangle with sides AB and hypotenuse C, you will always have that A squared plus B squared will equal C squared. And the proof that I'm going to use is actually extremely amazing and does not actually require any fancy math. It only requires a bit of drawing. So that's what we're going to do. Oh, I wanted to go to the next page by doing that, but instead I made a line. So let's just do that. Okay, 2, we're on page 2 now. Oh, wait, no, we're not. Now we are. Change, set the background. Jamboard. Okay, so remember what we're trying to do here? We're trying to prove the Pythagorean theorem, right? So we have the theorem, which is, Pythagorean in its nature. And now we have the proof. Okay, so consider a how am I going to do this? I wrote down somewhere. Yes. Okay, so let's draw our very first triangle. Yes. Oops. So we know that the triangle we're looking at is ABC, where this is a right angle, right? Okay. Now, what I'm going to do is I'm just going to reorient the triangle in several different ways, and it's going to create something that's quite interesting. So what do we mean by that? Well, let's take this triangle and rotate it such that the hypotenuse is facing down. Okay. So if I do that, then my hypotenuse is here, and then my right angle is here, and my sides AB are here. Okay. Now, what I'm going to do is I'm going to do the same thing, but now I'm going to make my my hypotenuse be going vertically down, but facing to the left, or to the left of the screen, right? So what I mean by that is, I guess I should make this almost to scale. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Right. So again, this is C. But now because I've rotated the triangle clockwise, A is now here. Okay. A is now here, and then my right angle triangle. Sorry, my right angle is here. Right. Okay. So A is here, and now B is here. Okay. Now you guessed it. I'm going to do the same thing, but now my hypotenuse is going to be facing up. right? So I'm gonna do another counterclockwise turn, and my hypotenuse is going to be here. Okay, all right. So now what happens again to the other two sides, A and B? Well, let's see. A is going to be here now. So A is going to be here now. And then B, that's definitely not a right angle triangle anymore. But it is, right? Because there's a symbol. Is going to be like this, right? So imagine this is a straight line. Of course, this needs to be a straight line because um, I've rotated my triangle 90 degrees with respect to the previous triangle. So of course the line should be still straight, right? Because if I have something like this, yeah. So right, this is at a right angle, and now I rotate this, I guess 90 degrees. Then it's going to look like this, and it's going to be here. So of course this line, this is a straight line. Straight line. Okay. All right. And again, I'm going to do again the same thing. I'm going to rotate clockwise the triangle 90 degrees. I'm pretty sure, yeah, this is a 90-degree rotation every time, which makes sense. If you think about it slightly more in a slightly more in-depth manner, because there's, anyways, that doesn't matter for the purposes of this video. Right. Okay. So anyway, C is here now, right? C is facing to the right, right? Or like it's anyway. You see what's going on. A lot of preparation has gone into making this video. So now, where are my two sides again? Well, this side A is going to be here, and this side B is going to be here, and again, it's going to be a right angle here. Okay. Cool. Now, let's take a look at what we just did here. Okay. So, what did we just do? What is the point of what I'm doing here? Yes. Yes. Okay. So you notice that actually what's going on here is that this is one small square. So we have the small square, C, right? And then we have a larger square, right? We have a larger square, but that's just been tilted by 90 degrees, right? So really, if we put the square back to its position we're all used to, it's going to be a square of side A plus B, right? So this is side A plus B, A plus B, A plus B. So now what I'm going to do is I'm going to compute the area of this larger square in two different ways. And because of course it's the same square, it's going to be the same area, right? So what I'm going to do now, right? So now I will compute the area of square 2 in two different ways. And these two results will be equal because the areas will be the same. Okay. So how am I going to do this? I don't want to go on a different page because it's quite illustrative to have the example here. So I think I'm going to do it here. Okay, good. And I'm going to change color, which I'm going to use blue. So what's an obvious way of computing the area? Well, it's a square. It has side A plus B. So the area of the square is just the square of its side, right? So the area of the square is equal to the square of its side, of the length of its side, right? And so A plus B squared, what is it if we expand this out, right? Hopefully we all remember that this is A squared plus 2AB plus B squared. Okay, so that's one way of computing the area, right? So let's say this is a square 1. Let's put it in a small parentheses to make it nice. Okay, what's the second way of computing the area? Well, let's think about it. We know that this is a big square, and it's composed of this smaller square, and actually of four triangles, right? So we have this first triangle A, this second triangle B, this third triangle C, and this fourth triangle D. Okay. So we have four triangles. They're all the same, right? So if they're all the same, they all have the same area. So then what we could do is we could say the area of the whole square is just the sum of the area of its parts, right? So we have, we're going to take the area of, so the square 1, right? Plus we're going to take the area of the triangle A plus the area of the triangle B plus the area of the triangle C plus the area of the triangle D, right? But all these four areas of triangles are the same. So I could just say that this is equal to the area of the square 1 plus 4 times the area of the triangle. Okay? All right. Excellent. I see I'm running out of space, which is unfortunate. So what I'm going to do is I'm going to erase some of this here because I think we don't really need this anymore, right? Like we don't need to know what a straight line is. Well, it's always good to know, but we don't need to see it to believe it. I don't like silences, so I like to speak while trying to, do things. I like to avoid silence. So while I'm erasing, I've already finished erasing, but there's a bit of a lag. So I'm just watching myself erase. Okay, right, all right, okay, that's enough. Okay, very good. Okay, excellent. So now, okay, now what do I need to do? I need to compute the area of the small square, right? So the area of the small square 1, that's going to be the square of the length of its side, right? And the length of the square 1 of square 1 side is C, right? So that means that its area is C squared. Okay. And then what's the area of a triangle? Well, the area of a triangle is, base times height over 2. Base fois hauteur divisé par 2, as we say in the Quebec. So maybe base isn't the right term in English, but that's how I say it in French. So anyways, you don't care about this. So what's the area of this triangle in particular? Well, its height is A and its base is B, and we divide that by 2. Okay. So now what happens if we put this all together? We have, putting this all together, we have the area of the square, the second way of computing it, is the area of the smaller square plus 4 times the area of the triangles. Well, 4 times the area of the triangle. So what is this if we put this all together? It's C squared plus 4 times A times B over 2, right? And so if we simplify this, we cancel out the 2, then we get C squared plus 2AB. Okay, so remember what the initial point of this was, right? It's here. Whoops. The initial point was here, right? We're going to compute the area of the square 2, right? The larger square, in 2 different ways. And because we're computing the same area, these 2 results will be equal, right? So what that means is that now I have that the area of the square 2 computed the first way is equal to the area of that same square, but computed a different way, right? And so what happens if we replace these 2 things? We get a squared plus 2ab is equal to, plus b squared is equal to c squared plus 2ab. Okay, so now all we need to do here is let's cancel out this 2ab here. And the result we get is that a square plus b squared is equal to c squared. The desired results. Amazing, fantastic. When I first saw this proof, I got so excited because this is such an elegant way of proving this result. And so you can see that this applies to any ABC in general, right? Of course, we just have to assume that in this case, ABC are part of the reals, right? And for our sake are positive. But once we have that, then in general, if we have a right angle triangle that looks like this, then we always have this property that holds. And that's seriously amazing, folks. Um, yeah, so that's why 25 is cool. Well, 25 is cool because it's the very first Pythagorean triple that are whole integers, right? Um, so 25 is part of that 5 square. But then it's also cool because it inspired me to show you this proof, which I think is even cooler. But arguably the 25 inspires the proof, right? Because you could have done this proof just as easily if this had been 5, this had been 4. What did I say? Whatever, it doesn't matter. 4 and then 3, right? This proof would have worked. I mean, it would have been for a specific case, and you would have seen that 5 squared would have equaled 3 squared plus 4 squared. But this is just a generalization of this result. Okay, well that's all I wanted to share in this video. So I hope that this has showed why 25 is not interesting, cool. And I think I have exclamation marks. Yeah, right. So well, it's been a pleasure. And I will see you in the next video thing. Okay, stop recording.